In this video, I'll be solving problem 6.3, which states find the force of attraction between two magnetic dipoles M1 and M2, oriented as shown in figure 6.7 here. They are a distance r apart, and for part A, we're going to use equation 6.2, and for part B, we're going to use equation 6.3. I've also brought in the general definition for the magnetic field due to a dipole, and I should note that this equation works only for a dipole in the z direction at origin. In a previous chapter, problem 5.34 proves that this equation could be rewritten as the equation on the right here. And in order to get from here to here, it just takes some manipulation of dot products and understanding how you're going to get rid of these cosine and sine terms. So I'm going to be using this equation on the right here throughout this problem in order to solve for the magnetic field due to M1, the dipole. Or if we start with part A, and so let's look at equation 6.2. So what you'll notice in equation 6.2 is that we have an I and an R here. There's no definition for M2, right? There's no magnetic dipole anywhere in this equation, and so how are we going to get M2 in here? And the way we're going to do that is we're going to model M2 as a circular loop of wire. And with a perfect dipole, like we have defined here as M2, we have the radius of the loop, big R, is going to be much smaller than the distance from the dipole, little r. Right, that's our distance here. So it's going to be an infinitesimal loop that we're modeling M2 as. And so I've drawn a figure here, which is kind of dramatized, right? This is not infinitesimal, but it allows us to see each of our components and what's going on here. Like I said, we have M1 at the origin, right, pointed in the z direction. And I've modeled M2 here as a circular loop of wire with current I and radius r. And we have this r vector pointing from the dipole to the edges of this circular loop. And at each of these edges, the B field kind of points outward and up from the loop. That's here. And I've also defined r hat here close to B and y hat here close to B. And that'll be helpful later. I've also defined phi and theta here, these angles that will help explain our geometry. We want to obviously solve equation 6.2. And the big ticket here is finding out what B cosine theta is. So if we look at the figure again, B cosine theta, well, that can be modeled as the dot product between B field and y hat. Right, and you can kind of prove this to yourself, right? The definition of the dot product is going to be the magnitude of these two equations multiplied together, and then multiplied by cosine and the angle between them, which is theta. And we've just proven that. And I'm going to bring down this definition of our magnetic field due to a dipole. In order to get B cos theta, we want to dot this with y. So dot each side with y. And this is going to become B cos theta by the above definition. And we are left with this thing to evaluate on the right-hand side. So let's distribute the dot product first. And so in the brackets here, we're left with a couple of dot products that we could evaluate. I think the easiest one is here on the end. We defined M1 to point in the z hat direction, and therefore this is going to equal 0, right? Because M1 is confined to z hat, and z hat dot y hat is 0. Now let's look at M1 dotted with r hat. Definition of phi helps solve this dot product, right? So we have the magnitude of these two equations, or sorry, these two vectors multiplied together. So there'll be 1 here for the r hat, but I'm just going to omit that. And then we have cosine and the angle between them, which is phi. So next we have this r hat dot y hat. Oops, r hat dot y hat. This one is a little tricky, but if I kind of scale up the geometry here of what's going on with, actually here, let's do this. If I scale up the geometry here, and we focus on what's going on up in the top right, we can use vertical angles and say that this is also equal to phi. The goal is to find this piece, right? So this piece can be defined as sine of phi. So now we can continue evaluating B cos theta, now that we've evaluated those dot products. I'm going to plug those in. And we're still not done yet. We can simplify this down a little bit more. So let's look at how we can define cosine phi. So cosine phi, if we look at our geometry here, we can define this length as the square root of, oh, actually, that's wrong, sorry, of little r squared minus big R squared. Right, that's Pythagorean theorem. That's a classic. And so cosine phi, we can say, is equal to following. And remember what I said before, right? We're modeling M2 as a circular loop of wire where big R is much less than little r. And so in the case where big R is much less than little r, this value in the square root is going to be approximately equal to square root of r squared, which of course is just equal to r. And therefore cosine phi, whatever, is going to be equal to r over r, or we should write that as 1. Now, for sine phi, we have big R over r, little r. But now that we have these definitions, we can plug that into our equation once again. Yeah. And I'm going to rewrite this a little bit more neatly. But your result for B cos theta should match something like this. Okay. And now let's go back to our force equation, equation 6.2. Now that we've defined B cos theta, we can plug that in. And I forgot to, I was going to mention this up here, but it works just fine. M2, when we model it as a circular loop of wire, it's going to be I dA. That is going to, if we want to write the magnitude of this, that is going to be, we get a pi big R squared, right? Because dA is going to be, dA is going to be this, the integral of dA is going to equal the area of the loop here. So that's where we get the pi R squared. So that little definition there is going to help us break down our force equation. So I want to get M2 in here somehow. So let's take out pi. Let's take out our I, and we got an R squared there. Perfect. So I'm going to multiply this by M2. And I'm also going to reduce this 2 up front and move that to a 2 in the denominator. So now let's rewrite this more neatly. And thus this equation, the force is going to be our answer for part A. Now on to part B. And bring over the important equations here. Okay, now the nice thing about this equation, equation 6.3, is that we have a magnetic dipole within it, right? So we're allowed to model M2 as it is, as a dipole, right? Let me bring down the figure here as well, so we really get a clear picture. And again, we need these dipoles to cooperate with me for one. Right, we need these dipoles to be on the z-axis. Right, we put M1 at the origin. Consider B along the z-axis, right, due to M1. Because that's what we're ultimately going to solve here, right? We're going to solve B at M2, and M2, of course, is along the z-axis. So let's get a general equation for B along the z-axis. Right, so R is usually equal to R hat. This is going to turn into Z hat. Right, the radial component is aligned with the Z hat component, or it's aligned with the z-axis, however you want to state that. So that's how I'm going to transform this equation into something more usable for the force equation on the left. So we say that B then is, and remember that M1 and M2, they both point in the z hat direction, right? And so this dot product is going to be pretty easy to get rid of here. And I'm also going to replace M1 on the right there with M1 z hat, like such. We can simplify this down even further. Right, we have inside the brackets here, we have 2 M1 z hat. So that 2, I can reduce the 4 up front, right here. And then we have a 3 showing up, and also M1 up here in the numerator. It's a little messy, but that is going to, or not 3, excuse me. Right, that, I don't know why I thought that, but I was looking at this 3 here, and then I remembered that this is equal to 2 M1 z hat, and we already canceled that 2 out right down here. This is a good definition for our B field at any point along the z-axis, right, due to M1. And, right, we already wrote this definition for M2, but I'm going to rewrite it. Right, you'll notice that both of these equations are in the z hat direction. And so when we take the dot product to calculate for our force here, let's do this over here on the left. When we take the dot product, z hat dot z hat is, of course, equal to 1. And so we can multiply the magnitude of these two equations together. And then we're going to take the gradient. Make some space for that. We're going to take the gradient. Well, this should have a vector on it, I hope. I'm missing it up here. That's okay. Anyway, that should have a vector on it, because when we take the gradient, it is going to result in a vector quantity. So, of course, force on the left-hand side here is going to be a vector. So let's continue evaluating. And so we're going to take the gradient of what's inside the parentheses here. And notice we only have a z-dependence, so these constants are going to come out front. That's from our gradient definition. So we end up getting... So that is our equation for the force at any given z. And if you remember from the geometry of our problem, z is going to be equal to r. And so z is equal to r at M2, to be clear. So I'm just replacing that z to the fourth with an r to the fourth, and we are still in the z hat direction here. And that is going to be the answer to part B. And we can sort of check ourselves here, right? We saw the magnitude in the first part, so let's see if our magnitudes check out. And you'll see that we have a negative up here at the top, but overall, the magnitudes of these two equations are equivalent. And so we got to be doing something right. So thank you. That is problem 6.3 solved.